Good afternoon, ladies and gentlemen. Welcome to our SESAR Digital Academy webinar today. My name is Olivia Nunes. I'm an ITM expert at the SESAR joint undertaking. I'm very pleased to be hosting this session today. Our aim is to provide the public, everybody, the opportunity to learn about what's going on in SESAR firsthand from the people who are working on it. So our topic today is the smarter, safer, and more efficient arrivals. Before getting into the topic, though, I do want to share some housekeeping information with you. First of all, I want to say this is actually part 2 of this webinar. We had another webinar in September. So all our previous webinars are replayable, and the Q&As are also available. And you can access them in our SJU page, in the sesarju.eu page, in the past events or replay past webinars, as you can see. And then you can download the presentations, as this one will be available as well. Okay. Then next thing to say, pretty important, is that we do have a lot of people connected. It's fine if you want to chat, that's fantastic, but we cannot monitor. You cannot ensure that we monitor all the chat. So if you have questions, please do put them on the questions so that we will be sure that we can read them. Some questions will be answered in writing by the speakers, or sometimes there's someone behind, like from their team, that can answer as well. And some questions will be answered afterwards in the live Q&A session that we will be having. And any questions that maybe are not answered in one or the other, they will be answered after the session. And we will upload this Q&A file together with the recording and the presentations to this past webinar page, so that it's available for the future. And I think that's all I want to say. These are our speakers. We have 3 speakers that are on stage right now. Frédéric, Pierre, Yves, and Gunnar. They will be speaking in this order. So first, I want to welcome Frédéric. So Frédéric Roseler has an aeronautical engineering degree, and he has a safety background, and he has worked for over 20 years in civil aviation and air traffic management. He works at Eurocontrol. He is the part of the airport unit from the network management operations, and he's coordinating the deployment support to high-performance runway solutions, many of which have been developed in SESAR. You know, the SESAR program has been already running for I think about 13 years. So in recent years, Frédéric has been involved in particular in the weight recart, time-based separation, runway status lights, leading supporting safety cases and working with stakeholders for initial deployments. And he's now acting as DREAM's project work package lead and solution expert for the enhanced approach procedures. And that's the topic of his presentation today. So Frédéric, the floor is yours.
Yes, thank you, Olivia. So good afternoon, everyone. So indeed, today I will present you 2 operational solutions, which development has been led by Eurocontrol in the recent years, obviously working with various partners coming from as ANSP or aircraft manufacturer, research organization, and industrial actors under SESAR. These solutions are in fact addressed in 2 projects, in particular in the current Wave 2 activities, Project 2, as well as DREAMS, which is the Very Large Demonstration 1 project. And now, of course, I'll invite you to understand further what it is about and the activities that have been undertaken. So let's start with the ISGS, or Increased Second Glide Slope. So as we can see here, the idea is that the solution would enable a combination of a conventional approach angle, but also a steeper approach above and active as well. And that would be flown by part of the traffic. So here we basically expect to have operation in a mixed mode. And when we speak about steeper approach, in fact, we would...
Frederick, we don't
Yes.
see your presentation. I don't
sorry. I'm sorry for that. Let's try this. Can you see it now?
Not yet.
Is possible now?
No.
No. It's really... I'm sorry for that. I'll try again. Okay, I'll close and restart. Yes. Can you see it now?
Now we do.
Okay.
Perfect.
Okay,
Thanks.
great. So yes, I was saying about the increased second glide slope. As I was saying, the idea is to combine a conventional approach, segment, and a final approach, which is steeper profile, and this will be operated in a mixed mode. So part of the traffic would fly that steeper approach, and we limit then the slope to maximum 4.49 degrees, which would somehow exclude what we call steep approach operation and associate need for specific certification. And so this second increased glide slope can be flown with GNSS, so satellite-based navigation, and the goal there is to achieve noise reduction for the final approach for the traffic which fly obviously steeper and higher. The second concept is the second runway aiming point, or we call it SRAP in short. And here the idea is to land further on the runway, again for part of the traffic, so it's also in mixed mode, and also can be supported by advanced satellite navigation. But here the goals are multiple. Not only there would be an expected noise reduction thanks to the shift of the final approach profile towards the runway and towards the airport, but as well there would be benefit associated to reduction of wake separation, so therefore leading to possible increase in runway throughput, or flying further on the runway would enable to reduce flight time by getting faster to the parking position, or depending on the runway configuration, reduce the runway occupancy time. And we could also combine the two, so the increased glide slope to the second runway aiming point. This is a third solution, which we call IGS to SRAP. The overall naming of these solutions is under enhanced approach procedure. In fact, the work started earlier on SESAR, already in SESAR 1, through the EAP enhanced approach procedure enabled by GBAS, and then further in the SESAR 2020 in Wave 1, as well as continuation now in Wave 2. So on the increased glide slope, second glide slope applicability, there is a key aspect to consider. If we have successive traffic flying on the steeper approach, in fact, we can apply standard separation even for wake turbulence. However, there is a situation where the number one traffic would be flying higher and number two on the conventional. And in that case, there can be a potential increased exposure, which would lead also, in some case, depending on the combination of aircraft, to increase the wake separation. Which means that, in fact, in this situation, and considering this, the IGS solution and operations are in fact compatible with limited traffic pressure, but also we could limit as well that impact through use of optimized wake turbulence separation schemes like RPAS. But that also means that overall, we expect this solution to be more applicable for lower traffic levels like off-peak or night situations, but it's also where we can expect the most constraint from the noise point of view. If we look at the SRAP and IGS to SRAP, so with the double threshold, so here there is also a potential impact if number one traffic is above, but there is here as well a big benefit when we have smaller aircraft flying higher than larger aircraft, which would remain on conventional approach. And you can optimize the wake separation. It depends also on the distance between the two thresholds and the two aiming points, which also create the vertical distance between the glide slope. But there is a possibility, if we apply here in the example to the wake recat scheme, to gain a further 1 or 2 miles in some case, and even ultimately possible suspension of the additional wake separation. So the optimum working method here is to assign the smaller aircraft, medium and light to the SRAP and to the upper glide. So here we can gain runway throughput benefits, arrival throughput. We estimate between 2 and 6% because it depends on the traffic mix and the proportion of aircraft which fly on the SRAP. But it's also very much dependent to achieve a high usage of the SRAP glide and avoid mixing the configuration. And therefore, we need to target a combination of advanced approach navigation techniques, GNSS, for example, GBAS, but also SBAS. And again, the benefit will be larger when we operate with more refined separation schemes like recat. So this concept is therefore here applicable for peak traffic and of interest to airport hubs in particular. So how do we intend to operate this enhanced approach procedure? So it all starts with the publication stage. Each procedure, being the SRAP or the increased second glide slope, are published procedure. So they are in unique identification, one per approach type, and we can also publish the specific characteristics regarding the slope or the aiming point location, or the second threshold. Of course, there is this multiple approach procedure being simultaneously active. And so, of course, as well, the flight crew needs to be aware of the specific characteristics of the procedure, not only through the charts, but also through familiarization, through airport briefings, and possible simulation sessions. And then tactically, so the approach procedure which are active would be mentioned and displayed on the ATC, and the pilot can, from that, prepare and brief the most expected approach. Then at initial contact with approach, they would be receiving the expected approach procedure, which can correspond to the approach they briefed, or otherwise they need to rebrief in case. And they can always reject if one of the procedure is not found suitable, eventually given the specific conditions of the flight. There is a possibility to revert to conventional approach to a certain stage, but of course, this needs to be done early enough for the aircraft.
Your presentation has gone again, I think.
That's strange because I can see it like before. So again, I'll try to. Reset, sorry. Can you see it now?
Not yet. And actually, now we don't see you either. I don't know what happened.
It's really strange. Okay, I'll do it again. I think there is indeed some jump.
Now it's back.
Okay. So I was saying that there is possibility to revert to conventional approach at some stage, and eventually the final approach controller will manage the separation management between the aircraft, also the speed profile aspect, because it may depend on the slope angle. And finally, the tower controller will ensure the monitoring of the traffic as they do, management of go-around, as well as specific reminder in the landing clearance about the intended threshold when applicable. So to summarize, in terms of the key enablers, we have on the ATC operation side, the need to be able to manage multiple active approach procedure, and there can be some interface HMI support for that. I will show examples, and the need to manage in particular the wake turbulence separation impact. On the airport infrastructure side, the adaptation of the visual aids, such as the slope indicator, the runway markings, or the approach lighting system. And on the flight operations aircraft side, it's published procedure. There is, of course, a key aspect on familiarization side and the pilot cockpit assistance for possible increased slopes depending on the aircraft type. So let's have a look at the ATC side first. Here is an illustration of adaptation of the controller HMI, which relies, in fact, here on the use of another SESAR solution, which is time-based separation and optimum runway delivery tool, which provide the controller with a spacing and separation indicators. And the flight labels of the traffic can basically be used to insert the assigned procedure such that the tool is aware of which profile and which separation applies. There is also some specific safety net that have been considered and identified as necessary, because of course the reduction of wake separation is relying on the fact that the aircraft will fly on different glide slope and different vertical profile, and in case there would be a interception of that profile, there is a need to warn the controller and to act directly. So there is this, what we call the glide alert warning information. And eventually, on the go-around side, there is one specific situation where number one traffic flying on the lower glide would do a missed approach. Then we lose the criteria for reduction of wake separation. And so if this is already the case, there is a need to manage go-around for the following traffic. And so this, in fact, has been evaluated through a series of real-time simulation with air traffic controllers. First in the SESAR 2020 Wave 1, where there was an initial focus on the nominal case, on the controller HMI, and the use of this TBS ORD tool. And then in the Wave 2, where we look then at the non-nominal situation, such as the go-around or the failure of the tool or the glide alert and the way the controller can manage this situation, plus specific phraseology as I introduced before for the second threshold operation. So let's now look at the other enablers regarding the visual aids infrastructure. So let's start with the increased second glide slope, where in fact we have envisaged different solutions and design. So you can see here a first one, which is in fact a combination of two PAPI, one on the left, which is used for the standard approach profile, typically 3 degrees, and then one on the right hand, which is for the steeper approach profile. And here we use, in fact, as you see, standard colors, white and red. Now, there is another version which has been considered, which creates a slight difference between the two PAPI in order to minimize potential confusion. And here we replace on the right-hand PAPI for the steeper approach, the white standard white color by green color. So I now propose to have a look at what it will looks like through our flight simulation campaign. So we did a series of flight simulation campaign with here an Airbus 319 aircraft type with a full flight simulator qualified, and as well with a type-rated pilot from airline operators. And so I now show you a first video which shows the approach with increased second glide slope, 3.5 degree with this 319 with the dual PAPI solution. And this is in night condition.
300, 100 above. Check. 200. Minimum.
Continue.
100. 50, 40, 30, 20, retard, retard, retard.
Spoilers. Reverse going this way.
Okay, so that was then for the standard.
Frederick,
Yes.
we don't see you. We see the presentation, okay, but I don't know
Okay.
your camera.
It should be on, but okay, that's strange. Sorry for that. So I propose we move on with the presentation at least.
Yes, go on.
So now this is a picture of the same conditions, night conditions with the dual PAPI, but now with the, as you can see on the right hand, with the green and red. And we can go to the next video, which is then in fact showing the same but on the daylight conditions. So this is approach to Munich airport environment as we select as an example, and to the runway 08 right. So
Papi sieht aus wie geputzt.
Das habe ich erst überlegt, aber
Papi looks
das stimmt gar nicht. Check.
300. 100 above. 200. Minimum.
Check.
100. 50, 40, 30, 20, retard, retard, 5,
Spoilers.
okay, so let's now look at basically the main conclusions from this. So from the pilot perspective, the second PAPI was found useful and accepted. And in fact, there was a slight preference for this new color coding with the red and the green for the second PAPI. So let's now go to the SRAP, second runway aiming point. First, let's look at the runway markings and how we can accommodate the second threshold aiming points and touchdown zone. So in fact, there are two situations. It's either we have the second threshold, which is located more than 1,000 meters further. In that case, we can in fact duplicate the markings and avoid interference. So the first option was just to have a duplication of standard ICAO and X14 markings. Then we looked at a variant for the aiming point, which is using a checkered design. And in fact, this is inspired from what has been done at some airports. And it's still, I think, today the case in London City for the aiming point. We also look at the possibility to use another color to increase the distinction, but however, this was also more challenging for the pilots, as I explained. And eventually, the possibility to use a letter for the second threshold instead of an increment. And also the case where we have less than 1,000 meters about using the side of the runway shoulders also with markings. So let's have a look at the next video, which is now looking back at the first option, which is the duplication of ICAO markings. And again, still same port environment.
400.
Check.
300. 100 above. 200. Minimum.
Continue. Check.
100. 50. 40. 30. 20. Retard. Retard. Retard.
Spoilers. Reverse green, SESAR. Checked.
Okay, so that was to assess the runway markings when landing on the second threshold. And from the pilot perspective, in fact, there was a preference to keep white standard color for the markings single stripe for the touchdown zone, and duplication of ICAO. And they were not found disturbance by using the second markings, even landing on the first threshold. And so finally, the next key aspect is now at the approach lighting system that would be necessary as well to be adapted. So here we have looked at two main options. The first one is called steady or static, when you can see here we have a duplication of the standard approach lighting system, eliminating both thresholds simultaneously. And a second option would be to introduce a dynamic version, which would be switching. And so that would be only showing the approach lighting system for the next landing, depending of its intended threshold and aiming point. So either on the first threshold only or on the second threshold. So now we can look at another video again. So here we'll be landing on the second threshold, and this is the static versions with the lighting on. Okay, and so now let's look at the next one, which is obviously looking at the dynamic version. So here we can see that if we are in a sequence of arrivals, so in fact, our aircraft is assigned to the second threshold. However, in front, there is another traffic going to the first threshold, so on the lower glide. So in fact, we can first see the light for that traffic, and as soon as you will leaving the touchdown zone area, then the light will switch correctly to our approach. So let's have a look. We just saw the switch.
321, wind is calm, clear to land, runway 09 right, second threshold. Flight 321, clear to land, 09 right, second threshold. Check.
Land.
Check.
300, 100 above.
Check.
200. Minimum.
Continue.
Check.
100. 50. 40. 30. 20. Retard. Retard. Retard.
Spoilers. Reverse screen. Teaser.
All right, so this was to illustrate the lighting system. And in fact, the pilot feedback from these was that there is a preference for this switching configuration, in particular for lower cloud sailing conditions. However, we expect that obviously this is more complex to implement. We were thinking that we can take advantage of technologies such as runway static lights, which are already having dynamic lighting on the runway, automated and based on surveillance information. So that could be the ways to support this. And there were no disturbance reported regarding the other markings aspect. So from this, we'd like to introduce now the ongoing activity as part of the VLD1 project DREAMS, where in fact it's the continuation of the work through a series of flight trials. So for the ISGS solution, increased second glide slope, there are two campaigns which are going to take place. One in Frankfurt with evaluation of GLS Cat2 with a 3.2 slope. And then in Roma Ciampino, with the participation of Dassault and Honeywell in particular, with the Embraer 170 aircraft, for evaluating 3.9 and 4.4 slope on top of a baseline of 3.5 approach, and this with RNPS bus procedure. And for the second runway aiming point, a first series of trials took place, in fact, earlier this month at Twente in the east of the Netherlands, where there was the evaluation of the marking solution as well with GBAS, GASD, ground station, and support of noise analysis. And through that was achieved with different aircraft platforms, the NLR test Cessna aircraft, as well as two operators from TUI and Lufthansa, as you can see, with Boeing 737 and Airbus 319 aircraft. So this is the setup that was implemented in Twente with the dual threshold and the markings and the second PAPI facing the eastern direction of the runway. And you can also see here the team involved from NLR and Eurocontrol. And now we can have a look at the final video, which is now an approach to the second threshold at Twente, seen from the NLR aircraft. So the advantage that we had from this Twente trial is that it's a non-commercial airfield, so we had more flexibility to organize this trial, obviously, and it was already quite useful as well to compare to the flight simulation environment, in particular regarding the external light conditions, which may influence the visibility. And one of the key aspects, for example, was the visibility of the two PAPI to make sure that both would be sufficiently visible and with the same level of brightness. And finally, some last picture here from the trial, from the three participating aircraft platform. We had the three aircraft that mostly flew the SRAP with a 3-degree parallel profile, while the Lufthansa aircraft 319 was flying mostly the 3.5 approach type. And luckily, we had sufficiently good weather conditions for these initial trials. So last, and to close this, I would like to highlight that there is in fact a call for project which was published already in mid-September, a Connecting Europe facility call. And this includes, as some of you may have be aware, a call for the SESAR digital demonstrator, with the DSD project. One of the groups are linked to the green operations, and in the topic are identify the IGS and the SRAB solutions. So in case you are interested in by this concept, by this solution, and to contribute to prepare deployment with large-scale flight demonstration, obviously there is a great opportunity to continue the work, and Eurocontrol is also willing to participate with partners. So you can always contact me, and so we will gather interest from the ATM partners on this topic. So with this, I would like to thank you for your attention, and I leave the floor back to Olivia.
So thank you very much, Frederick, for this very comprehensive presentation. It was really interesting. You can stay on stage if you like, or you can step out.
Yes.
We have many questions with quite some detail, so you may want to take a look at those.
I will.
And I would ask Pierre to step on stage, please. He's our next presenter. So welcome, Pierre. So I'll introduce Pierre briefly. To say he's actually an engineer with a background in navigation systems like GPS, Galileo, GLONASS, and synthetic vision as well. It's synthetic and enhanced vision. He has over 20 years of experience in the aviation industry. He works for Thales Avionics, and he has been involved in SESAR projects since almost since the start, since 2009. And he's actually working now with a focus on future operations, and that's very much what we like in SESAR. So he's gonna talk to us about the use of geometrical altimetry in the last phases of the approach, which is a topic that's less mature than we have just seen, and I think really fascinating for me. Please, Pierre, the floor is yours.
Thank you, Olivia. Okay, I guess you can see the presentation.
We do.
Perfect. Okay, so I was told there has been an excellent presentation on geometric and barometric altimetry. I think it was 1 year ago on a similar webinar. So of course, my goal is not to reinvent this presentation. I will rather focus on a concrete application, which is the use of geometric altitude in approach phase. But first of all, maybe, well, I guess all of you know that we are using pressure to compute altitude in aviation. But have you ever wondered what's the exact difference between a barometer and an altimeter? Well, the exact difference is that we use, let's say, a translation model, which is an international standard atmosphere model to translate from pressure to altitude. This model, you can see here, is actually a theoretical model, which provide pressure and temperature value versus altitude. But the exact relationship between the baro and the geometric altitude are never accurate, and they always depend on meteorological context. So it could depend on the pressure and temperature at sea level, and also it could depend on the temperature profile. In some rare cases, for example, we can experience temperature inversion, which means that at higher altitude, we will have warmer temperature than at a lower altitude, which is quite unusual, but can happen. So what you have just to keep in mind is that without proper correction, an altimeter rarely provides the exact geometric altitude. So, well, how do we fly today? I guess all of you know there are two cases. Either we are far from the airport and we fly high enough, so all the aircraft share the same setting, the same altitude setting, which means exactly the ESA model. So they assume the conditions are equivalent to ESA model, and this is enough to maintain the vertical separation because all aircraft have the same reference altitude. Of course, it's nothing to do with the actual geometric altitude, but we don't mind. However, when we are close to the ground, then in this case, we need to stick to the geometric altitude to have obstacle clearances. So in this case, we add a barometric correction, which is named Q and H, which is transmitted by ATC in order to correct the altitude setting. Having a look at the impact of baro pressure and temperature on geometric altitude. Well, if you look at pressure variation, if local pressure is above the ESA model, then the real altitude will be above the barometric one. So here you can see that for the same reading, altitude reading on the altimeter, well, you will have different actual altitude in the actual altitude because of different pressure conditions. And this is compensated, this is corrected by this QNH compensation. So you use this knob here on the altimeter, and by looking in the window, you can just offset the altitude. We have actually the same issue with temperature variation. So if local temperature is above the ESA model, the real temperature, the real altitude, sorry, will be above the barometric altitude. But you have to keep in mind that this is not compensated. So how do we do? How can we fly? It's because usually approach procedures account for this temperature error. They add margin, so down to or up to a certain temperature value, you are safe. You can just fly with your, let's say, wrong altitude. You're okay. So usually, in countries with mild climate, pilots are not used to compensate because they don't need to. They are safe. But if you fly to northern countries in wintertime, then you will have to compensate if the ground temperature drops below some expected value. In this case, to compensate, there are more or less two ways to do it. Either the ATC just clears the aircraft at a higher than normal altitude, or more commonly is done at aircraft level. The aircraft or the pilot offsets the published altitude to remain safe. Well, how do we do that here? An example of an operational use is a landing in command base in Alaska. And if we have a look at the FAA documentation, we see that there is a minimum temperature which is published. So I know that above this minimum temperature, above -21 degrees, I don't need to compensate. But if the temperature drops below, then we have to compensate. And here, with a different phase of flight, we have to compensate. So here, it's only in final approach. Looking at the approach chart, we have a reminder of this minimum temperature here. And in the approach profile, we have here the different altitude constraints that we have to meet during the approach phase. This altitude constraint will have to be offset by this temperature compensation. There is an altitude constraint here, and there is also what we call decision altitude or minimum decision altitude, which is the altitude below which one the crew is not supposed to continue the descent if he can't see the runway. So all these values has to be offset in order to remain safe. And this offset can be done either manually by the pilot or by the flight management system, by the avionics. Well, okay, so you could say we have a process, and so there is no issue, we can just compensate. Yes, that's true, and at the same time, there are some limitations and there are some drawbacks for the temperature compensation. Well, as you imagine, incorrect temperature information could lead to catastrophic consequences. So you have to be extremely careful when you input the temperature input by ATC. We also talked about temperature inversion. In this case, you have no way to know it, but actually, at least what happened is that your flight path angle will become steeper than expected. And this is never a good idea, especially when you are close to the ground. And well, in this case, you also have some additional workload for the crew. And in some cases, you do not have temperature information because there is no ATC on the airport you are going to. So the only solution is either to divert to another airport or to use more conservative value. You can just use temperature information from the nearest airfield and add margins. But if you really want to remain safe, you have to add so much margins that at the end, you might just go around because, well, you will not be able to see the runway in time. Finally, in some cases, if you compensate the temperature in intermediate phase, it means that you will offset your flight level or your altitude. And by offsetting this, you may, in some cases, disable some approach modes of the avionics level. So this is a nightmare. Either you want to remain safe in the intermediate phase, for example, and you are not able to conduct the final approach phase, or if you want to conduct the final approach phase, you may not be safe during the intermediate phase. So all this leads to kind of safety issues. Safety is one point. There is another point, which is the optimization of the profile, of the flight profile. If we are looking at a traditional ILS glide intercept, usually it's performed from a constant altitude. and the glide will be acquired intercepted actually from below. Any error on the barrow altitude will just end in a, let's say, uncertainty on the final approach point, which is this point where you are supposed to acquire the glide. So you will acquire it later or sooner, but anyway, you will still be on the glide. So you could say, well, okay, it's not a big deal. Yeah, you may be right. But let's have a look. If we look now at an optimized descent. Optimized descent, it means that you are not coming from a constant altitude. In this case, any error, and especially in hot temperature cases, will make you arrive above the glide. Arriving from above the glide may have some drawbacks. If you want to get on the glide, you have to, again, have some steeper flight path angle, which is not a good idea. Some other point that some autopilots are not well designed to acquire the glide from above. So either they will just need some really good stabilization phase, or sometimes they will never intercept the glide. And anyway, okay, you still have this stabilization phase that could be at least 2 nautical miles to be on the correct ILS. So, well, now let's have a look. What can we do to get rid of temperature compensation? Because we see that it drives a lot of issues. We want to use a geometric altitude. So geometric altitude could be used in a new type of approach procedures. They are new, but not so new. Actually, this is the exact same procedure as before, but we have just introduced a transition from barometric to geometric altitude much before the FAS. So what happens there is that the aircraft will no longer follow the barometric guidance, but a geometric guidance, which will be performed by GPS. You will follow GPS altitude until you arrive on the final approach point, and you will arrive exactly where you expect to, so you can intercept the glide with absolutely no uncertainty. You will see also that this optimizes the lateral approach profile. The GPS, as I mentioned, is an enabler, but GPS by itself, unfortunately, does not provide integrity on the vertical axis. To have integrity and the expected accuracy, you need to use what we call satellite-based augmentation system, or SBAS. SBAS use additional GPS correction, which are transmitted by other satellites. But this SBAS has limited coverage. We have SBAS above the US, above Europe. Sometimes we also have it above India, above Japan. But you can see that the coverage is limited. And even if the coverage is not, well, you can see, okay, it's limited, but sometimes even if you're under the coverage, you do not have the expected performance to perform the approaches. Yes, this is for LPV, okay, LPV, well, you do not have the expected availability, only, for example, 95% of the time. So this is something that has to be considered. And as you know also, well, jamming can still happen for GPS. So we have to find some, let's say, backup means. Another thing is that the GPS provides altitude which is referenced to ellipsoid. It's named WGS84, and it's just a simplified model of Earth, but which is different from the geoid reference or mean sea level reference that is used by the altimeter and by the procedures. So we have to add some kind of conversion from ellipsoid to geoid in order to use the GPS altitude directly inside the aircraft. This is named geoid ondulation, and it can either be embedded in the avionics as a model, or this could be data available in the published procedure, as it is today for LPV procedures, for example. Having a look back at our traditional glide intercept with this transition from barometric to geometric, we have here this additional phase, and we are sure that when we arrive on the final approach point, we are exactly where we expect to. So it means that this final approach point could be actually closer to the runway. This is also true when we talk about the optimized descent. Here we will have our convergence phase, and here still arriving at the final approach point, which could be much closer to the runway. And we have just removed all our issues of safety, of acquisition from above, and so on. Now let's have a look. How can we optimize the lateral profile? Imagine we have this current procedure, some kind of no-fly zone, you are not supposed to fly over. And due to the stabilization on the glide, you have this extra margin here on the final approach point. So the only way to perform this approach is to go on the right here at this barometric guidance, acquire the ILS here, and end on the runway. Now, what we plan to propose and to test is this new procedure. We still have the barometric guidance, but we introduce this transition from barometric to geometric here. And since we are geometric, we can arrive on the ILS beam much later and have the final approach point much closer to the runway. So you can see that we have reduced the number of track miles because we could not go on this part. We just went on the left part of the no-fly zone. An additional point is that, well, you could also additionally optimize the vertical path by extending the 3-degree glide path through the curved segment here, because you have 3 degrees here, but since you are already in geometric in this case, you can just have 3 degrees as well. It will have a more stable and deterministic vertical path. Of course, well, everything is nice, but life is never perfect, so there are still a couple of challenges at ATC level. ATC will have to manage a mix of barometric and geometric reference traffic. This is quite unusual, so we have to look at it with extreme care. The instructions that could be transformed by ATC, for example, just level off, go around, anything like that should still remain in baro. So sometimes you have a transition back from geo to baro, and this is also to be studied. Of course, we need, or ATC need to guarantee that the actual vertical paths are there to altitude constraints. And this drives a question. Does the aircraft geometric altitude has to be sent at ground level? Today, only barometric information is transmitted to ATC. Do we need to also transmit geometric altitude that in some case is already available, for example, in IDSB? That's a question we have to discuss. Also challenges, for example, when you are designing the procedure, you have this vertical constraint here, and the pilot has to check that he is at the correct altitude, or at least above these altitudes. But here, we are in barometric. We have not started the transition phase yet. And here, when geometric, the transition is there. So how do we indicate to the pilot that this is geometric and that is barometric? We have to look at it more carefully. Of course, the avionics has to provide a smooth, accurate, and safe transition, that's for sure. And the pilot has also to change its mindset because everything in the cockpit is referenced to baro. So if suddenly we just change to geo, we have to make sure that the pilot is aware of that and there is no ambiguity about the cockpit information. And finally, we could extend this concept not on new procedures, but on existing procedures. It would only improve the capture rate, probably not optimize the profile, but it could be interesting anyway. So that's more or less what I wanted to say with you to you. And so if you have any question, we'll be happy to answer. Thank you.
Thank you very much, Pierre. Very, very interesting presentation, very technical, I think. You do have some questions coming up. Like before, you feel free to stay on stage or just step out. And then we'll welcome you later anyway. And, I wanted to welcome on stage our next speaker, Gunnar, please. So Gunnar Schwag, here you're good. Gunnar Schwag is a scientist at the German Airspace Center, DLR, in the Institute of Flight Guidance, and he is now working mainly on drones. So I think he's doing both the integration into the air traffic, and also looking at more the missions and what can be useful in terms of the deployment, for instance, of unmanned aircraft or drones in crisis situation to enable real-time situational awareness. I'm not sure what that exactly is, but you're in drone land, let's say. And just to say, I was excited to see he graduated in mathematics. Like I told him, like me, there are not so many of us in the industry. And he is the coordinator for the expert research project viercart. viercart is our project that's looking at how to integrate RPAS in the TMA. So we know that there are additional challenges where we have different projects looking at integration of RPAS in en route, accommodation, which is what we call what can be done today. And I would say Gunnar's project is like the one that's looking at the hardest part, which is the TMA, and what to do with the drones when they want to be actually in the arrival sequence in the TMA, potentially intertwined with manned aircraft. Gunnar, the floor is yours.
Thank you so much, Olivia, for the introduction. I could also talk about situational awareness in real-time in crisis situations, but today I will talk about integration of RPAS into the arrival stream. I will also briefly touch upon the other parts of our project in viercart, because they just belong to the concept itself. But yeah, I try to focus it a bit on the topic of today's webinar. So let's see if that works. It does. So if you're not very used to the term RPAS, I will briefly introduce to you what we mean with that. I know there's sometimes a bit of a misunderstanding when you talk about drones or unmanned aircraft systems or remotely piloted aircraft systems. So what we focus in that project in viercart is the remotely piloted aircraft systems, in the sense that they are a subset of the unmanned aircraft systems family, let's say. And every RPAS is controlled by a dedicated remote pilot, certified remote pilot on the ground. So we're talking about bigger aircraft, usually bigger aircraft. You have some examples in the pictures, so you might see some of them from the military side. You can see the Dornier 228, which we operate at DLR as optionally piloted vehicle, and we control it from the ground as well. But you could also imagine, for example, a Boeing 737, which is modified to be enabled to be flown from the ground or operated from the ground and piloted from the ground in future cargo operations, so to say. So the challenge is here to integrate those kinds of aircraft into ATM system, just as manned aircraft with a remote pilot on the ground. As you can already see in the pictures, there are differences in the airframes, let's say, so different weights and different wake turbulences that come from that have to be taken into account. We have other aspects for communication and command and control links and latencies attached to that. So we have to consider that when we try to derive a concept for the integration of such RPAS. I will talk about all of those topics later on as well. Yeah, I lost focus, sorry. Off my mouse. Why do we have to do that? So why should RPAS be included in the arrival stream at all? Why don't we just go along with the current procedures, blocking airspaces and airfields and operating RPAS from there? As you might see in the surroundings, civil application of RPAS in particular, and also drones in the broader sense of urban air mobility, for example, is growing. So we expect to have a growing market of drones and RPAS in the airport infrastructure as well. One potential use case, as I said, with the Boeing 737 assumed cargo transport that can be enabled to be unmanned, which is a, let's say, imaginable use case in the future. We have crisis response and search and rescue activities, for example, that can be then operated from a regular airfield. You could imagine enabling communication infrastructure in remote areas and deploying multiple RPAS. Monitoring of infrastructure is one thing. Also, infrastructure on or in the airport vicinity, runway inspection and border inspection, railways, for example. Atmospheric research would be another one. So the use cases are broad. And the market is growing, so integration is required at some point in time. And as I said,
you could take dedicated airfields or blocked airspace, but that is not always practical. What is the difference? How do we get from the left-hand side of a regular manned cockpit with two people in the cockpit, pilot and co-pilot, to the pictures which are remote pilot stations on the right-hand side of the screen? The path is different. Let's say remote pilot stations can be different. So we have a quite high-level remote pilot station in the upper right corner, which is operated by mouse and keyboard only. So the remote pilot controls the aircraft with mouse and keyboard in this futuristic-looking thing. You have a bit more conventional-looking remote pilot stations in the other pictures. Notable difference is you cannot see what's going on outside. It might be the case you have cameras, but you don't have the outside view per se. You don't feel the aircraft, so your situational awareness is lower. And for example, you can see telephones. That is a, let's say, upside of the transfer, that you might have a landline communication to ATC and do not have to rely on your voice communication through radio link. Yeah, with the transfer comes higher automation, or sometimes different automation, you could say. So this has to be taken into account, the different automation of RPAS, also when it comes to arrival and landing phase and runway vacation. And all of that is covered, unfortunately, by the fact that latency comes into play. So communication might carry a bigger latency, and in particular, command and control link latency to the aircraft itself. That is one big issue, and that is why I want to highlight that on this slide. There are different architectures thinkable. So you can see the pictograms taken from ICAO manual on RPAS. You might have seen them before. They are on the topmost row. You can see the radio line of sight architecture. So the remote pilot station is in radio line of sight of the aircraft in the air, of the RPA. And you have some latency to control that. And you have communication with ATC, with also radio communication. Some latency is attached to that. Satellite communication is one other possibility. So if your RPA is far away from your remote pilot stations, you might have to rely on satellite communication, which is a big addition to latency factors. And if you don't have radio connection to ATC, you might relay that through the RPA, which then also is in the latency number or range of the satellite communication. And the row on the bottom, there is ground communication installed, and we think this is not only feasible but also realistic, and we think this could help to have safe operations if there is at least a communication landline to ATC for the remote pilot, and if it happens to have a connection to the RPA because it is in the airport vicinity for the arrival, you could route that through the ground communication. Now you can see some numbers, ballpark numbers, maybe to highlight the control latency of 2 seconds when you go via satellite communication, which is a two-way latency number. And our experts said, well, if it's 2 seconds only, you're lucky. So you could even expect to have bigger latency there. So of course you want to stay low in low latencies. So you might want to pick the most reliable and less latency affected connection for your operations. What else do we have as integration issues? There is a magnitude of possible airframes for RPAS. You don't have to have the space for a pilot in there, so they might be small or light. You can see the watchkeeper in the fourth column as a very slow and light example of what could be IFR capable, but is a big difference to, for example, a modified 737 on the right with much higher speeds and much higher weight, and yeah, coming with that wake turbulence. So if a watchkeeper follows a 737 on the glide slope, the distance should be bigger than usual, than in usual operations, IFR operations on airfields. Plus, there is the latency aspect that comes on top of that. So the metrics will change, will have to change, and that will have also an impact on runway throughput. We are assessing that in the project as well. So runway throughput will be measured, and we expect that. So our simulations are upcoming, but we expect that to be lower. But we also try to see if the equity can still be ensured, so that RPAS are neither favored or the opposite. Some more operational challenges, not yet finished. We researched nominal operations and non-nominal operation aspects, and what can happen in RPAS operations and what is a new addition when you operate RPAS. So even in nominal operations, you have challenges by increased workload due to some latency on both sides, remote pilot and ATC. As I said before, you lose some situational awareness because you're not in the aircraft, you cannot feel the aircraft. A part of that is the fact that we, in our concept of operations, we said you shouldn't use visual aids for your control of the RPA during the landing phase. Because due to latency, you could give the wrong input to the system, and then you have pilot-induced oscillation, and your arrival is not smart anymore and not safe. And yeah, so you shouldn't rely on that. That's why we think an automatic takeoff and landing system should be in place. As I said also before, reduced airspace capacity can be expected. In non-nominal operations, we have additional factors that come into play when you operate RPAS. For example, tooling failure, that is an unmanned, let's say, aspect, and ATOL failure that you can see under that, so automatic takeoff and landing system. If that fails, or if a subsystem fails, what then? Again, a step back towards the scope of our project. So our aim is to develop a concept of operations, shortly abbreviated to CONOPS, to integrate those RPAS into existing ATM environment and infrastructures within the TMA and airports under instrument flight rules. We focus on the marked flight phases, so taxiing from your parking position to the runway, and then departure via standard instrument departure. And then we leave out the en route sector because we think it's least critical, at least in our scope. And then for the approach and arrival phase to a safe landing and taxiing back to your parking position. We have a special focus also set to the impact of latency. As you saw, the numbers can be quite high. So what is the impact of that latency? What is required for an automatic takeoff and landing system, and how can that be operated and should be operated? How can you realize a handover between remote pilot stations? Because you can ensure a more or a safer arrival and landing phase if you have the control handed over to a distinct remote pilot station in the airport vicinity. I will come back to that later. And we look at airspace classes A, B, and C in IFR, as I said. We had to take some assumptions, and we started with Eurocontrol's RPAS traffic class 6. I will not read everything out loud, but it's based on EASA's certified category, opposed to open and specific, so certified operations under instrument flight rules. And you have to meet some performance requirements, in the network TMA and airport. You have to be capable of flying SIDS and stars. You have to be able to meet communication, navigation, and surveillance airspace requirements. There needs to be two-way communication with ATC in place. You have to be able to contact ATC if your link is lost to your RPA, if you have an emergency situation, or as a final resort, controlled termination of flight. You have to have and detect and avoid equipment on board compatible with ACAS, and a flight plan needs to be attached to that operation, so including type of RPAS, your planned contingency procedures if anything goes wrong, and a contact phone number, backup landline phone number to the remote pilot. And that's not all. So we found some more assumptions we have to take. We assume the RPA to be of a fixed wing structure, which is, we don't really exclude rotary winged aircraft if they can fly the SIDS and stars and if they are able to meet the requirements, feel free to use them. But we said, yeah, usually they have different procedures, so fixed wing structure is an assumption at least. They have to be certified adequately. They have to have a command and control link. And then for the landing phase, arrival and landing phase, a system which I reasoned before that is capable to perform a landing without relying on visual aid. If you have a big latency, if you happen to have a big latency, you cannot ensure safe landings anymore. So the automatic takeoff and landing system should be in place, and you should be able to leave the runway on your own. So there is no gain in having an RPAS land automatically and then blocking the runway because some towing vehicle needs to come out and pull that off the runway. So for an efficient integration, it needs to have taxi capabilities. Some preliminary findings. So we are halfway through the project, and we will have simulations in November, and we will have a second iteration of our concept of operations and our requirements. But we have some preliminary findings already. Regarding the handover, as I said, we think it is likely to happen that a handover to a distinct remote pilot station in the airport vicinity will happen. You don't have the problem of latency when you have a bigger flight and you have to rely on satellite communication with that in the en route phase. You would want to switch back to radio line of sight or even ground communication with ATC in order to have a safe operation in the airport vicinity. We realized there are some system requirements with that and some operational requirements. So yeah, the remote pilot stations must be active and the C2 link must be compatible, and you have to have voice communication between the remote pilot stations. And then for the actual handover, you have to take into account the status of the RPAS, the location, any changes to the RPA or the flight plan, and what is not favorable. But if you have any ATC instructions that are still pending while you're doing the switching, they should not get lost. For the coordination with ATC, a backup number, as I said before, landline connection, should be also in place, either direct or through some center. Then we have a big set of requirements, almost 100 preliminary, that is, requirements divided into operational and functional parts that was derived from our initial concept of operations. You see some examples here for ATC, for example, And for the handover procedure, they are numerous, they are required. We tried not to repeat anything or everything, let's say, that stems from manned aviation. So we say, if it's possible, please stick to manned aviation requirements. But there still are many additional ones that we stumbled upon. Yeah, and all of that, so our initial ConOps and the initial set of requirements will be validated in the real-time simulations upcoming right now in November. We couldn't do everything that we identified, so we had to put a bit of a focus on the most crucial parts. Let's say topmost is impact of latency on air traffic control and the remote pilot. We look at nominal conditions, and then we look at communication link failure, what happens, transponder failure, how does ATC react to that, and what if the RPA needs to perform a traffic avoidance maneuver in a traffic conflict situation, and again, with latency attached to that. Then we have a closer look at the arrival and landing phase with an automatic takeoff and landing system. We first will look at nominal conditions. Then what happens if an ATOL subsystem fails? So they are failure safe, but there can be ATOL occurrences. That's how they are called. And if a subsystem fails, what can we do then? What is if there is a conflict on the runway incursion, and you have to perform a go-around missed approach with latency maybe to the command, and what happens if your C2 link fails? And then we look at multiple RPAS at the same time in the approach phase, first in nominal conditions, and then what happens in an assumed case C2 link fails for all of them for some reason, attack or infrastructure breakdown. So what happens if 3, 4 RPAS are affected at the same time, and where do they go and what do they do? And last but not least, we will look at the coordination of a handover between 2 remote pilots and ATC. We have a distributed simulation, so 1 remote pilot station in the Netherlands and 1 in Germany that will perform this handover. So it is rather realistic, let's say, to hand that over to a very remote person. So we even have latency already by covering that distance. And that's about it. As I said, we are halfway through, so you can find our first set of documentation, the public deliverables on initial concept of operations, on use cases, and on state of the art on our public webpage, viercart.eu. You can check the SESAR Joint Undertaking webpage. We're on Cordis. And you can follow us on LinkedIn and Twitter. And of course, you can write me an email at any time. Thank you so much.
Thank you very much, Gunnar. You can stay on stage. I'm just going to ask the other 2 speakers, Frédéric and Pierre, if you can come. And we're going to start our Q&A. We're running, unfortunately, a little bit late, but we'll try to make the most of the time we have. And we've had, I'll start with Frédéric. Many questions saying, well, how is this different from what we had before? Because we have some places like London City that already have like an increased glide slope, and we have had displaced thresholds before. So how would you summarize what is different from what we had before?
Yes, so I tried to answer some of these already in the question in the chat. So for the steep approach, in fact, first the concept is I increase second glide slope, so it's not an increased slope, but it's a second glide slope in addition. So there is a mixed operation, and then for London City, indeed, a lot of people refer to that case. This is a very steep approach. It's a 5.5 degree. Here we limit to 4.49, which is basically in the range of approach for which aircraft are already certified, such as, for example, business jet in particular. So there is no need for special additional certification. For the SRAP, indeed, and that's quite a common feedback we received, that there was indeed the well-known trial of HALS DTOP in Frankfurt in the early 2000s. HALS DTOP is the high landing approach system and dual threshold operation. So from that trial at that moment, it was applied to Frankfurt to parallel runways, the 2.5 left and right at the time. Now the right runway became center since, but it was to take advantage already indeed of the difference in the glide slope between medium aircraft and heavy aircraft, and then to reduce the wake separation. So the principles are the same. The difference here is we do that on a single runway, and we couple to other benefits, in particular the reduction of flight time or runway occupancy time, depending on the runway configuration. And also, we understand that there were some challenges at the time, in particular for managing the complexity of the procedure. And since then, now, typically, we have developed and work on time-based separation where there is a controller separation tool, and the tool can be adapted to support this second runway aiming point operation and multiple approaches. So that are kind of new elements since.
Yeah, thank you very much. That's, I think, a very comprehensive answer. I would like now to go to Pierre and ask you, we've had quite a few questions saying, but this is very complicated. You have to do the FMS and the navigation database, and is it really, you said yourself, you have to consider that the whole cockpit is set up for barometric, and it seems like a massive change. And the question I have for you, you already answered. Well, you can save, let's say, miles, and that's good, and there's increased safety. Do you also see this as a step towards, let's say, proceeding to geometric in other areas? I mean, like higher up, or do you think that this would stay for some specific airports where it's very hot, and that do you foresee that everyone would fly around the approach in geometric, or do you think that it will stay a mixed thing, let's say?
Well, I think the first step would be to deploy this on airports which are, of course, which have problems with temperature compensation. So yes, that's the first point. But as I mentioned, you could also deploy this on other airports, because you may still have some issue with intercepting the glide. I mean, if you have not correctly corrected, I mean, the altitude, or even if you are still in the expected temperature range, you may still be slightly above or below the glide. So this would improve. This would definitely improve the capture and the safety. And just to answer what you said at the beginning, it does not change that much. I mean, if you compare to today, if you have to compensate for an approach compared to what you will have in the future, where just selecting the correct procedure from the cockpit point of view, it's really easy. Just select the point of view and the procedure, and then directly the aircraft will do the job. So for the pilot, it's really much better. The complexity in the cockpit is not so high, because you already have usually the SBAS or GPS with SBAS. The FMS is not so complicated to add this function. So I think it's really an improvement.
And do you foresee that eventually, after this first problematic airports, that could be like the standard way to land everywhere, that you transition higher up, or do you think that's a difficult question?
I wouldn't say that. I mean, as I mentioned, there are still a lot of challenge to overcome. So yeah, first, what we're studying is let's say the easiest way to have geometric altitude. You have this transition, and at the end you want to intercept a glide. So okay, this glide, it exists somewhere. If you have no glide, then okay, it means more or less you are trying to do some kind of LPV approaches, and then you will have all the problem of SBAS coverage that we mentioned before. And if we want to go higher, then the question is how do you mix barometric and geometric altitude? You have to change all the reference for all the aircraft at the same time to keep the safety. So that's not so easy. I mean, and there has been also some question regarding RPAS. Yes, RPAS usually are reference to geometric. So that's a topic.
You mean that it would facilitate in separating, or if you have RPAS so little drones usually around the airport, they fly geometric, and then you would be able to maybe have a common reference for both one way, for example.
Yes, I mean, if the aircraft is sending both altitude, geometric and barometric, then it could help to make the separation with RPAS and other aircraft in barometric. So that's probably something we'll go to.
Okay, thank you very much. And then I'll go on to Gunnar, and the question I have for you is, I think that you said one of the preliminary conclusions was that it would actually have to be, to actually integrate it's not a dedicated airfield, but it's an airfield where I am landing with my with my airliner, and then just behind or just in front of me there is an RPAS, and that they would have to be radio line of sight, probably, to avoid all these latency problems. And what does this mean? Does this mean that they would have to have like a base at the airport, or can you just go voice over IP for it's radio line of sight, but you have an antenna at each airport, and only airports with this equipment would be able to accept the RPAS? How do you foresee that?
Mm-hmm.
What's the
good
idea?
question. Thank you. I think the possibilities are, you could have both, depending on how much improvement you want to have on your airfield. So if it is a really dense airport and you have to optimize, or you want to optimize your arrival stream, I think there's no way you can not have a remote pilot station that is dedicated to that very airport. The remote pilot could know the surroundings very well. He knows the procedures that are in place. So I think the efficiency would be much higher if there is an airport centralized remote pilot station that RPAs can connect to, and then the remote pilot station has maybe even looks outside the window and sees his RPA arriving with a low latency radio line of sight. If you do not want to have that optimization, maybe there is another possibility, what you said before, but I think, yeah, the most practical and safe assumption would be to have a remote pilot station right next to the airport, knowing everything of their surroundings.
And the second question is that you keep hearing about this C2 link, and you can imagine that around the airport maybe there is there are more obstacles and it's kind of harder. Is that going to be the exception, or we really can expect that the C2 link is going to be failing all the time? And you basically once the aircraft is, I don't know, below 5,000, you just have to let them, you just have to clear them to land, because you risk, it's too risky, and they may have a C2 link, let's say.
Well, I think
how frequent do you? I see your assumption. Let's say.
I would say from my exploratory research position point of view, I would hope that this is a technical solution that can be taken care of in the future. So I would not expect, or I would, not expect to have C2 links that fail regularly to be allowed for such IFR operations that we envisage. But yeah, I think that is technologically wise quite a step in the future. And I would, for now, just rely on technology that will lead us there.
Okay, thank you. We have almost no time left, but I would like to just give each of you the opportunity, if you want to say something else that maybe I haven't asked, but from the questions that were there or that came to mind. So first, Frederick, any closing remarks you may want to do? Now is the time.
Yes, no, just maybe to remind the last slide I show, which is basically the digital sky demonstrator call, which is published at the moment. And so again, there is an opportunity to continue the work on these solutions through that new call of project to go to larger scale demonstration. And so, yeah, that's a logical next step on the work that has been done so far.
Okay, thank you very much. And for you, Pierre, is there anything that didn't come in, and maybe I came up in the questions and I didn't say?
Well, just to say that at the moment we are in, let's say, exercise test. So we have full flight simulator testing, and well, what we would expect is to have flight test probably the next phase of the project. So we will see, but that would be the next step if we can continue this way.
You mean in how long from now? Let's say you
I
expect
don't
to
know.
be fly. Let's say,
I
like
don't
in the
know.
air.
Couple of years, maybe 2-3 years.
Okay.
I don't know.
Okay. No, just to get an idea of the magnitude. Let's say. Thank you very much. And for you, Guna, is there something that you would like to say as a closing remark?
Yeah, maybe. As I said before in my presentation, we will have our simulation campaign in 3 different places in the next month. So you can expect some more material that can visualize what I said before in the next week. So it may be worth checking out our channels. And maybe we will see each other again in a webinar when we have the final round of our documentation and the results in the simulation. So yeah, I would be looking forward to that.
Are most of your, let's say, deliverables or your output, is that usually public? Will it be available publicly?
Yeah, well, most of the, let's say, interesting stuff for the public, we have simulation architecture documents and whatnot, and a communication strategy, so that those are not public, but most of the interesting stuff will be made available on our website.
Thank you very much. So we'll stay tuned for that. Well, thank you, everybody. All I want to say is that we were running very late, so the Q&A session was not as long as we would have liked, but we're only 1 minute late. We do have a poll for you to, asking for feedback. And just to confirm, because someone asked, I guess they joined a little bit late, the slides are available afterwards and the Q&A as well. So we will distribute the Q&A file, not distribute, upload it with the slides. So you can have a full record of the session as well as the recording. We do know that a lot of people register, and then we actually have a lot of people playing back the webinar afterwards. And that's great, at your convenience. Thank you very much.
Thank you.
Thank you.
Thank you, everyone.